Hello friends, welcome to my YouTube channel. In this series of tutorial on shear force and bending moment diagram, today we are going to discuss a new problem on cantilever beam for gate purpose. Friends, the topic of SFD and BMD can be learned only through solving problems. I am going to upload 50 problems on SFD and BMD, and if you go through these problems you will never find any problem in future regarding shear force and bending moment diagram, especially in gate exam. The sign conventions are universal and taken from standard books. For more information on sign convention, refer to the link of the video in the description box. Okay, so we will start this video, friends. Now this is our problem. You can see this, friends. This is a cantilever beam, and on this cantilever beam there is a load W is acting over this extension here. Okay, now we have to draw the shear force and the bending moment diagram. But before that we have to convert this beam into an equivalent beam, okay, which will be simpler for analysis, which will be simple to analyze. Okay, now see this, friends. Because of this force W, there will be a moment acting over this beam in this direction. At this point the moment will occur having magnitude W into L. Okay, W into L. Now this movement will can be transferred further here at the point C in this direction having same magnitude WL. So the diagram will become like this. The equivalent figure can be drawn for this cantilever beam like this. I am showing here. This is the point A, okay, and this is the point B, and at the point C you can transfer this movement like this. I have transferred in the clockwise anti-clockwise direction, and also you can transfer this load over this point C here like this, okay, and it will act vertically downward. Okay, now this load can be transferred at the point C without affecting anything in this beam like this I have done here. Now friends, let us solve this problem for this cantilever beam. Now friends, the first thing that we have to find out is the reaction at the point A, that is the vertical reaction at the point A and the moment reaction at the point A. So the net force acting at the point, net force acting over this cantilever beam is how much? W, which is acting in vertically downward direction. So the reaction at A in vertical direction will be equal to this net vertical force, and it is equal to W, and its direction will be opposite to the F net, and it will lie vertically upward. So the vertical reaction can be shown here like this. So this is the vertical reaction acting RAB having magnitude W, okay, at the point A. Now the net moment acting at the point A we have to find out. So the net moment acting at the point A we have to find out. For that we have to consider this point A. Now about this point A, this load is causing a clockwise rotation or clockwise movement. So the moment will have of magnitude. These are the two length 2L. This is the 2L and this is the 2L. So the magnitude of the movement will be this load W into 2L plus 2L, that is 4L, and it will act in which direction? Clockwise direction. And this movement is acting at point C in anti-clockwise direction. So it will cause a movement of WL about point A, this movement in anti-clockwise direction. Okay, so this will cancel out to give us 3WL in which direction? In clockwise direction. Okay, now the moment reaction at A will be equal to net movement at A, and is given as 3WL, but will act in opposite direction to the net opposite direction to that of net movement, that is anti-clockwise. This is clockwise, so it will be anti-clockwise. Okay, Now I will show here the moment reaction at A. So this is the moment reaction at A, going in anti-clockwise direction like this, and its magnitude is 3 WL anti-clockwise. Okay, now friends, what we will do, we will calculate the shear force at the various points, that is the point A and C, because at point A there is loading and at C there is some load acting. That's why we will calculate the shear force only at these 2 points. So first we will calculate the shear force at the point A. Now because at the point A there is a vertical load acting and a concentrated moment is acting, that's why we will calculate the shear force at the point A on the left side of the point A, and on the right side of the point A we will calculate the shear force, because there is a point load acting at the point A. That's why we are calculating, because the shear force will change its magnitude when moving from left side of the point A to the right side of the point A. That's why we are calculating on the left side and on the right side of this point A the value of shear force. So to calculate the value of the shear force on the left side of the point A, we have to construct a section on the left side of the point A. This is the section XX. Now friends, we know that shear force about any section is the sum of all the forces either on the left of the section or on the right of the section. So we will here consider left of the section. You can choose the right of the section also, but I am looking on the left side of the section. So on the left side of the section there is no force lying because the beam terminates here on the left side of this section. I am rubbing this beam, okay, to make the concept clear, because it is creating a little bit confusion for you, okay, because there is no work for that beam. Now, so on the left side of the section you can see the beam terminates and there is no force lying, so there will be no shear force about this section XX. So it will give a shear force of 0. Now shear force on the right side of the point A we will calculate. For that we will follow the same procedure, that is we will draw a section on the right side of the point A, very close to the point A we will draw this section, and now on the left side of this section XX there is a force W acting having magnitude W. This reaction RAB was acting here, this reaction RAB in vertically upward direction. Okay, I am again increasing its length. This is the reaction RAB. So it will give a positive shear force of magnitude W. Why it is giving a positive shear force? Because this force W is trying to rotate the beam element which is lying between the point A and this section XX in clockwise direction. So this is causing a positive shear force, our sign convention. This is if this is the section XX. Suppose if this is the section XX, I am drawing the section here, and this was our point A, suppose, and this was the reaction acting over this point A, that is W. Then it is rotating this beam element which is lying between the point A and this section XX in which direction? Clockwise direction. That's why it is taken as positive. So this is coming to be plus W, and because of this concentrated movement there will be no shear force about this section XX. Okay, now shear force at the point C we will calculate, because a concentrated load W is acting at this point C. That's why we will calculate the shear force on the left side of the point C and shear force on the right side of the point C. So shear force on the left side of the point C if we calculate, then what we have to do, we have to again follow the same procedure, that is we have to draw a section on the left side of the point C, and very close to this point C we have to draw this section. Now look on the left side of this section XX, then you can see this on the left side of this section only this load is contributing toward the shear force at this section XX, and because of this movement there will be no shear force about this section XX. So on the left side of the point C, the shear force because of this load W will be equal to plus W. Why? Plus is taken, same conclusion that we have drawn earlier, that is positive shear force. It is causing positive shear force about this section X. That is clockwise rotation of this beam element A and this point, and this force actually is rotating the beam element which is lying between the point A and this section XX in clockwise rotation. clockwise direction with respect to this section xx, or we can say that about this point it is rotating in clockwise direction. Now shear force on the right side of the point C, if you want to calculate, we will again follow the same procedure. We will draw a section on the right side of the point C, but the beam terminates here. You can see that on the right side of the point C. So you can look on the left side of this section and see this force is acting and this force is acting, which are contributing toward the shear force. This is contributing toward the positive shear force, and this is contributing toward the negative shear force about this section xx. So minus W, and it will give us 0. Using the same sign convention, the negative, because of this load there will be a negative shear force because of this sign convention, because this load W is trying to rotate a beam element which is lying between the imaginary beam element which is lying between the point C and this section xx in which direction? Anti-clockwise direction about this point. Okay, so it is taken to be 0. The calculation will come out to be 0, that is W minus W, W this W, and this W is equal to 0. Now we will draw the shear force diagram. Now the shear force diagram will look like this. This is the point C, suppose this is the point A, okay, and at the point A the shear force is initially 0, and on the right side of the point A it is going to plus W, and at the point C it is plus W, that is same level, it is W, and on the right side of the point C you can see that it is coming out to be 0. So joining first point with the second, second to the third, and third to the fourth, we will get the shear force diagram. We know that above this line AC positive shear force will lie, and below this line AC negative shear force will lie, and the shape of this diagram between point A and C is horizontal line because there is no loading acting between point A and C. So this is the shear force diagram. Now we will draw the bending moment diagram. Okay, for sign convention you can refer to my video lecture. The link of those video lecture are available in the description box. I haven't yet uploaded the sign convention video, but as soon as possible I will try to upload those videos, so you will find that video, because my sign convention are very universal and it will help you a lot because they will never fail in any case and they are easy to apply. So you should watch that video in which I have explained these sign convention in a very easy way. Okay, now shear force bending moment diagram I will draw. So bending moment diagram, for drawing bending moment diagram I will find out the bending moment at the point A. Now because the concentrated movement is acting at the point A, that's why I will draw the bending, I will calculate the bending moment on the left side of the point A, and bending moment I will calculate on the right side of the point A, because the bending moment will change suddenly as going from left of the point A to the right side of the point A because of this concentrated movement acting at this point A. So first of all we will follow the same procedure to find out the bending moment of the left side of the point A. That is, we have to construct a section on the left side of the point A. This is the section XS constructed here. Now according to the definition of the bending moment at any section, it is the bending moment at any section is defined as the sum of all the moment either taken from the left, either taken on the left of the section or on the right of the section, right side of the section. Okay, now we will choose here the left side. So on the left side we can see that the beam terminates on the left side, that's why bending moment on the left side of the point A is 0. And bending moment on the right side, to calculate the bending moment on the right side of the point A, what we have to do, we have to again construct the section here on the right side of the point A. This is the section XS constructed here. Now you can see that, friend, on the left side of this section there is only this concentrated movement contributing toward the bending moment about this section XX. This force is not contributing to any bending moment because the distance of this force from the section XX is almost 0, because this section XX is lying very close to this point A. For your clarity I have shown it with a little bit distance, but it is actually very close to this point A. Now because of this movement, the magnitude of this movement is how much? This much, 3WL, and going in anti-clockwise direction, so it will be treated as minus 3WL. The minus sign is because of the sign convention. For concentrated movement, the minus, we will take this sign convention, that is a movement which is lying on the LHS of a section and going in anti-clockwise direction is treated as negative. Similarly, this movement is lying on the LHS of this section XX and going in anti-clockwise direction. That's why it is taken as negative here. Now we will find out the bending moment at the point C. Because a concentrated movement is acting here, that's why we will calculate the bending moment on the left side of the point C, and bending moment we will calculate on the right side of the point C, because the bending moment will change suddenly when going from left side of the point C to the right side of the point C. That's why we have to calculate on the both side of the point C. So for that bending, if we want to calculate bending moment on the left side of the point C, then we have to follow the same procedure. Okay friends, that is, we have to construct a section on the left side of this point C. This is the section XX, and we have to look for the various movements acting on the left side of this point C. So because of this force W, there will be a movement of W into 4L. Okay, W into this 2L plus 2L is equal to 4L, and it is creating a sagging bending moment about this section XX. That is, it is trying to bend this beam element A and between this point which is lying on the section XX, this beam element in concavity up direction, that is this type of, okay, that is sagging bending moment. That's why it is positive. Now bending moment, because of this concentrated movement which is acting at this point A at this section XX, will be treated as negative, that is minus 3WL, because the magnitude of this movement is 3WL taken from here. Okay, this is MRA is 3WL taken from here. So because of this the bending moment, using this sign convention that I have already explained to you, this section, this movement is lying on the LHS of this section and going into anti-clockwise direction like this. So it is treated as negative. That's why minus 3WL came here. Now on the right side of the point C, if you want to calculate the bending moment, and we have to rub this section and again follow the same procedure and draw a section on the right side of the point C. Now you can see friends, on the right side of this, if you look on the left side of this section XX, that you can find that this force is contributing toward a bending moment of 4 into W into 4L, W into 4L, creating a sagging bending moment. That's why plus, and this moment is creating a negative bending moment about the section XX using this sign convention, and this movement acting at the point C is also contributing toward the movement at the section XS, which is giving a negative bending moments of minus WL following the same sign convention, this sign convention, because this moment is lying on the LHS of this section and going anti-clockwise direction. Similarly, in our sign convention, this moment is lying in the LHS of this section XX and going in anti-clockwise direction. That's why taken negative. So if we find it, then you can see it is coming out to be 0. So now we will draw the bending moment diagram. So for drawing the bending moment diagram, we will rub this. Okay. Now see how I am drawing the bending moment diagram. Very easy. It's, you can do the same for the shear force diagram also, like projecting this line here, projecting this point here, and projecting this point here. Okay. Now what we have to do, we have to take a point here. It is A, it is B, and it is C. Now see here friend, on the left side of the point A, the bending moment is 0, so making cross here on this line, and on the right side of the point A, it is coming out to be minus 3W. So minus 3W will be down this line. Okay, here somewhere here, minus 3WL. Okay, and bending moment on the left side of the point C is how much? WL. So it is going somewhere here at the point C, above this point C, because above this line bending moment is positive and below this line bending moment is treated as negative. So third point is here, and on the right side of the point C the bending moment is 0. So fourth point will be here. So joining first point with the second, a second with the third, like this, and third with the fourth, we will get our bending moment diagram. Also friends, the shape of the shear force diagram between the point A and C is straight line. That's why the shape of the bending moment diagram between A and C is an inclined line. Okay, so this was all for today's topic, friend. If you like my video, you can subscribe my channel and also press the bell icon for the notification of the upcoming videos. So thank you, friends, for watching the video. This is WN. Okay.